This lesson is all about Newton's second law. Again, I've just included the section from the course content just so you can follow what needs to be covered. This is what is expected of you for this lesson: to recall Newton's second law, to recall and apply the equation, to estimate resultant forces acting in everyday accelerations. I will introduce you to this squiggle symbol, and then we will build on the term inertia that we learnt last lesson. The first thing I'd like you to do is recall what Newton's first law is, because by the end of this lesson you will see how these tie together really quite nicely. So it's really important that you do understand Newton's first law first. So to recap, Newton's first law basically says that for an object that is stationary or moving at a constant speed, it will remain in that state until it is acted on by a resultant force. So Newton's second law builds on that and lets us think about the resultant force that is acting on that object. There are 2 points that you need to consider. These are points that you are going to be familiar with as well. So although you know this, you won't realise necessarily that it is actually Newton's second law. So the first point that you need to be aware of is the larger the force acting on an object, i.e. the larger the resultant force, the bigger its acceleration will be. Put that into context. If you're riding a bike and you put more force through your legs to turn the pedals, then you will accelerate more than if you put less force through your legs. The second point to note is that for a fixed force, an object with less mass will accelerate more than an object with a larger mass. In other words, if you are still on your bike and you put the same force through your pedals, if you're carrying loads of bags, which let's be honest is a little bit hard on a bike, but if you are carrying loads of bags and therefore you have more mass, it's going to be harder to actually accelerate. So putting this together leads us to the formula where force equals mass times acceleration. Force, as always, is measured in newtons, mass is measured in kilograms, and acceleration is measured in meters per second squared. The 2 points from the previous slide can be clearly explained now and seen. So for a constant mass, the bigger the force applied to the object, the bigger the acceleration will be. And you can see that from this equation. The second point was for a fixed force. So if the force remains fixed, the bigger the mass, the smaller the acceleration must be in order for that force to remain the same. So as far as physics formulae go, this one is pretty straightforward. Force equals mass times acceleration. So let's work through an example. A car with a mass of 1,250 kilograms has an engine that provides a driving force of 5,200 newtons. At 70 miles an hour, the drag force acting on the car is 5,100 newtons. Find its acceleration at 70 miles an hour. Okay, so think, what have you got in the question and what is useful information? So the first thing to note is that 70 miles an hour is not relevant. Force equals mass times acceleration. There is nothing in that question about speed. Okay, so we don't need that. So let's have a look what we have got. We've got a mass. Okay, that mass is 1,250 kilograms. And we also have a couple of forces. We have a driving force, that's the force pushing it forward. And then you've got a drag force, which is resisting it, which is 5,100 newtons acting in the opposite direction. So what's the first thing you need to do? First thing you need to do is calculate the resultant force on the car. So how will you do that? So easy, the resultant force is 5,200 minus 5,100, which gives you an answer of 100 newtons. Having found the resultant force, you can use that in conjunction with the mass to find the acceleration. So rearranging the equation, you get acceleration is force divided by mass. We know the force is 100 newtons. Divide that by the mass, which is 1,250 kilograms. and you get your answer of 0.080 meters per second squared. I would take this time just to make sure you are happy rearranging the equation F equals ma. Make sure you can rearrange it to give you m equals and a equals. If you are unsure on what to do for this, watch one of my other videos, which is giving you pointers on rearranging equations. Okay, so another example now for you to work through yourself. So a car with a mass of 900 kilograms accelerates from rest with an initial acceleration of 2.5 meters per second squared. Calculate the resultant force required to produce this acceleration. Pause the video here to give yourself time to work it out. Did you get it right? If you remember earlier on in this unit, you had to learn typical speeds for everyday movement, such as walking, running, cycling, driving, etc. So you can use those along with Newton's second law to get an idea of the forces involved in everyday transport. Large forces are needed to produce large accelerations. So for example, if you've got a big lorry that's got a lot of mass, you're going to need a large force in order to accelerate it. So let's work through this example here. Estimate the resultant force on a car as it accelerates from rest to a typical speed in 10 seconds. So this is where I'm going to introduce to you this squiggly symbol. And this squiggly symbol means approximately. Okay, you can't use an equal sign, because an equal sign is a set value. This squiggle means it is approximately equal to. Okay, so you need to use it in this case because you are estimating the resultant force. You are not calculating it directly. So looking at the information you've been given, you've actually been given very little. All you've been given is you've got a time of 10 seconds through which the car is accelerating. So what do you have to do? First thing you want to do is estimate the acceleration of the car. How do you do that? Refer back to your previous lesson or a couple of lessons ago where you calculated acceleration, where acceleration is the change in velocity divided by the time taken. This is where you need to know your typical speed of a car. And your typical speed of a car is approximately 25 meters per second. If it's taken the car 10 seconds to reach this speed, then its acceleration is 25 divided by 10, which is 2.5 meters per second squared. You might be asking at this point, what other information have I got? Well, actually you don't. But here you need to do some more estimating. What is the mass of the car? So you should know roughly the mass of a car. It's around about 1,000 kilograms, okay, roughly a ton. So then you can use this and put it into your F equals ma equation. Putting it all together gives you 1,000 for your mass multiplied by 2.5, which is the acceleration that you have calculated from your typical speed of a car, which gives you an answer of 2,500 newtons. Remember, you are only estimating this value because you have estimated the mass of the car and you have estimated its speed. Okay, so you can say the resultant force is approximately 2,500 newtons. Building on from the last lesson where we introduced the concept of inertia and how hard it is to change the motion of an object, I'm now going to introduce you to an object's inertial mass. And this measures how difficult it is to change the velocity of an object and can be found by using Newton's second law. So you're using the exact equation that you've been using for this entire lesson. It's your turn now to work through some questions. You've got 4 questions on this slide, then you've got some answers, you can green pen your answers, and then you have got 4 questions on the slide after that. Work through those, pause the video where necessary and make sure you check your answers only after you've had a good go at them yourselves.